So this is the second experiment where we have to find the spring constant of a spiral spring by using method 1. So basically method 1, the principle is Hooke's law. We are using Hooke's law where the Hooke's law says that within the Hooke's limit, external force applied is directly proportional to the extension in the spring. So we know the formula, F is equal to minus kx, where k is the spring constant and x is the extension or the length under tension. Now nature of graph, if you are plotting graph, is f versus x. Since it's a linear graph, I can get a straight line, and the slope of that graph would be tan theta, which is opposite by adjacent, which is nothing but delta f by delta x, which is nothing but k. So that's how we will calculate the value of k, and this is the diagram. So you can see that F external is the force that is applied by external sources. This F is the F force produced in the spring, which will be proportional to F external. So that's basically what Hooke's law means. If F and F external are not proportional, then it's outside the limit of Hooke's law. Right, now I have already taken the values. I will demonstrate how to take the values now for the method 1. This is the observation table. First you have to make the reference. Reference means here is the apparatus. So basically reference means you have to take this out. Now what is the natural length? Where is the natural length of the spring? That's the reference. For example, the base of the spring, which is this one, is around 12 centimeter, as you can see. So that's my reference. So that is my reference. Now I have to keep on adding weights to here, and then I have to see what is the length. Now I have put 150 grams. I don't want to start from 50 grams or 100 grams, because at 50 grams and 100 grams maybe the spring may not be within the Hooke's law limit. So I'll start from 150 grams. So now at 150 gram, from the same reference point which I used earlier, now the extension I'll calculate, and it seems to be around 20.7. So that's what I have written here. So for 150 grams, so I have to convert it into newtons. So 150 into kg I have converted by dividing by 1000 into acceleration due to gravity, which is around 10. So I will get force. So 150 grams into 150 into 10 power minus 3 kg into 10. So for that, my extension or the length would be 20.7. So this is the length. Now what is the extension? So extension is the final length minus the initial length. So when I put 100 grams in the weight, 100 grams of weight, the extension was 17.5, or the length was 17.5. So the extension is 20.7 minus 17.5, which is 3.2. Note that this extension is supposed to be a constant, although experimentally it varies. Now I'll put 200 grams. So here I have put 200 grams now. So remember that each slotted weight is 50 grams. So at 200 grams, so let's see what is the length of the spring. So from the same reference point I'm seeing, and it's about 24 centimeter. Yeah, you can see it's around 24 centimeter. So that's what I have written here for 200 grams. So that means 200 into 10 power minus 3 into 10 newtons. 24 is the length. So then what is the extension? 24 minus 20.7, which comes out to be 3.3. So now similarly we'll keep on adding the mass. So I have added now 250 grams in total. So let's see what is the length now. So now the length is 27.4. Yeah, the length is 27.4. So that's what I've written here. For 250 grams, the length is 27.4 and the extension is 27.4 minus 24, which gets me 3.4. Likewise, I will calculate for 2 more 50 grams of slotted weight. Then my final reading would be 350 grams, that is 34.5, and the extension is 3.4. So you can see that this is the extension. Now I am not considering the first two readings, which is 50 grams and 100 grams. The reason is for those readings it may not be within Hooke's law. So I'll take from 150 grams and I'll take the average of extension. So I'll take this average. So when I calculate average, I'll get 3.38 centimeter. That is the average extension. Now if I calculate K is nothing but average of force divided by average extension, because we already know K is equal to delta F by delta X, right? So delta F is this one here, so which is basically 50 grams, that's the average, and delta X is 3.38. Now that's in centimeter, I have to convert it into meters. So 50 into 10 power minus 2, that would be the force, because it's 10 power minus 3 into 10 is 10 power minus 2, so it's 50 into 10 power minus 2 is the newtons is the average force, divided by 3.38 centimeters. So 10 centimeters 10 power minus 2, it goes up, it's 10 power plus 2, cancels off. 50 by 3.38 is 14.8 Newton per meter. This is my answer for spring constant. So if you want to plot the graph now, you have to plot the graph between force and length, not between force and extension, because extension is a constant, almost constant. You would get a straight line. So that straight line in the sense constant, like this. So you can't really calculate any slope there. So what you have to do, you have to plot a graph between force and length. Again, you can start from here or here, it doesn't matter. I have started from the first reading itself, so somewhere from here. I've started from here. So 150 grams and 20.5. This is the king. That means I can start from 20 also. I don't have to start from 1 or 2. But I have taken constant scale. So here 1 centimeter is equal to 2 centimeter, and here 1 centimeter is equal to 50 grams. So I have the points here. If I plot, I'll get almost a straight line. You may not get a perfect straight line. This is the weighted straight line, and the slope, if I calculate, so this length is 50 and this length came out to be 3.1. So 50 by 3.1 gives me the slope again K, which is 16.1. So from these two methods you can see that there is some difference. Now we'll come to the method 2, not 3, sorry, method 2. So basically method 2, we will be using this formula. What is the principle behind this formula? The principle is that the spring which will perform or will execute a simple harmonic motion. So from that simple harmonic motion, if we derive, we will get this formula where T is the time period. You have to explain in the exam, you have to explain what is T. T is the time period, basically it is the time taken for one oscillation. M is the mass, K is the spring constant. So I want K, so I'll solve for K, I'll get this formula. And observation pattern looks like this. So 3 observations are enough. So basically you have to calculate the time taken for 10 oscillations 3 times for 3 different masses, and we'll calculate the time taken for one oscillation, which is nothing but T by 10. We'll take the average and then we'll substitute here in this formula. So here I have taken 350 grams now. So I have loaded 350 grams to the spring. What I'll do, I'll just pull it. The extension should be small, don't pull it too much, and the extension should be in one dimension, not like this. So when I pull it in one dimension and let it go, it will perform simple harmonic motion. Now when the spring comes here, this extreme, I'll start the stop clock. So I'll tell you when I'll start the stop clock. I've started the stop clock. It's 1, 2, 3, 4, 7 and 10. So that's 10 oscillations. I have stopped the stop clock. The time taken is around 11. So first you have to know the least count here. So this is 10 seconds and this is 15 seconds. There are 10 divisions between. So each division is 0.5. So it's 11 seconds. So basically 11 seconds has elapsed. So that's what I'll write here. For 350 grams. So 350 grams means 350 divided by 1000. So it's 0.350 kg. And the time taken is 11 seconds. So obviously the time period would be 11 by 10. That would be 1.1 seconds. So similarly we have to do for at least 2 more masses. So now I have calculated for others also. I have taken more than 3 readings. So here are the calculations. So basically T, I have calculated T square and I have substituted in this formula. So I got 11.41, 12.8, 12.2, 15.65 and 13.2. So the reason I am taking more than 3 readings is some of the readings are way off. Say for example 11.41, that's way off. So I am not going to consider that. And also you can see that if I take the average of these two, of all this. So I'll get 12.8 plus 12.2 plus 15.65 plus 13.2. So it's around 53.85 divided by 1, 2, 3, 4 readings. So that will give me an average K of around 13.5 Newton per meter. So if you compare, so we got 14.8 there and we got 13.5 here and we got 16 there. So why there are so many differences? The one of the reason is, so I have used this stop clock. So the least count is 0.5 seconds. So if I get something like 5.3 seconds, I cannot make out here using this instrument. So that could be one of the major errors. So 13.5 and 14.8, basically they are almost equal, so we can say they are agreeing. The graph again is going some other value, it's giving some other value because it depends upon what kind of straight line you draw. I can draw 3 different straight lines using these points. So that could be one more reason. So this is the second method.